Okay, so now that we have this definition of a subgroup, let's look at example 2 and revisit our group UB7 from the previous example, example 1, and decide which of 3 sets are subgroups. And, well, we already kind of gave it away for 2 of them, but we don't really know about the third one. So let's look at all 3, just to really discuss this idea. When we're looking at, I copied the Cayley table for H1 right here, H2 and H3. So I wrote them down for all of those groups. You can convince yourself, or rather check if I did it right, but I think I did it right. So we have H1, which has elements 1, 2, 4, H2, which has elements 1, 3, 5, and H3, which has elements 1 and 6. And the question is, are they subgroups or not? Or is one of them a subgroup and another one not? So what do you think? Let's have a look at the Cayley table and decide. What do you think? What's the difference between the two? 3, actually. So when you're looking at it, I hope you see that for H1 and for H3, all the elements that show up in the Cayley table as entries are group elements themselves that are already in our subgroup. So 1, 2, and 4 are all entries that are in H1 themselves. And 1 and 6, that's all that shows up in the Cayley table for A3, and those are also elements that are in H3. So what's actually true here is that H1 and H3 are subgroups. Because they are closed under the operation, we have inverses, we have an identity element, and we have inherited associativity. But what about H2? So when you're looking at H2, there's something very different about it. In H2, there are actually 2 numbers that show up as entries that are not in the set H2 itself. And so that means that H2 is not closed, doesn't have closure. So H2 is not closed under the operation. And the operation, remember, was a multiplication mod 7. So we can see that 3 times 3, for example, is 2 mod 7, but that is not an element in H2, and so we don't have closure. That means that we can't have a group. So H2 is not a subgroup of U7.